about the consequences with seeing the bigger picture number 2, Andrzej Krzemieński.
So, hi again. Welcome to the second part on seeing the bigger picture when tracking for bugs in your software. For those who didn't attend the first part, you made a big mistake, but they are not related to one another, so it will work for you also. Does it work? Oh, let me switch it on. For a couple of years, I worked on a life-critical system, which was, this is what it's called in the industry, a weight and balance calculator. It is used to say whether an aircraft loaded with these people, their baggage, this particular cargo, and fuel necessary for the trip is safe to take off, whether it's not overweight, within a balance limits. If we do it wrong, we risk a couple of dangerous things, like a tail strike here. If it's too heavy on the tail when it takes off, this is what you get, and you don't want to do this. At the same time, it's not a real-time system. You do it on the side, use it like a calculator. So if it goes down, you just go to another station or do the same computation by hand, because load planners, the guys who are responsible for the job, know how to do it manually, and it's not that hard. So it will be in this context that we'll try to see a couple of bugs. So we'll be doing a couple of examples. One that I call a magic value, the other doing with exceptions. There will be also an exercise when I will require your input here. The main point is to show you how clever or too clever ideas to fix bugs only cause other bugs and don't help much. And all these cases deal with contingency. So all those cases where you don't have access to other system or server, or the connection to the database is lost, or this is something unexpected, and this is where most of the time the bugs lurk. It's probably because those parts of code are most difficult to get right. Also, we tend to put aside the thinking about them and focus on the main program logic, so they got lost. It's not that easy to test them also, because sometimes you cannot emulate all possible things that can go wrong. So you may ship a program, and the bug may be there for years before it gets discovered. And then, if you're not lucky, so imagine in a weight and balance calculator like this, that at some point we'll have to compute the total weight of everything loaded on an aircraft. We'll probably have some class, flight plan, which computes weight. We need to get to some implementation details, probably something from the database, so how the seats are laid out, what are the locations in the cargo hold of an aircraft. So we need to take these details, and we cannot see it from here, but we might suspect that because it's a pointer and it may happen to be null, there is some reason why this operation will fail. Perhaps we are using a lazy load optimization. We are loading all this data on the first usage, and because it's relying on the database, it may not work. If it works, we just use the guts to perform the computation. In order to make it short, I made it one instruction. Normally, it's something bigger. In the other case, and this is what I often see in the code, you type / to do, : need to fix it later, and you're done. And it can persist for months, years, go unnoticed. Know that this function is supposed to return type double. It returns nothing in this case, but it's okay. The compiler will eat it. Because, okay, unless you hit this path, everything works fine. When you hit it, you don't want to be there. It's likely it's either a crash or it will get you a random value, neither of which is very satisfactory. So at some point, somebody decides to fix this problem. He looks at all the to-dos. You do that, yeah? You look at the to-dos you write and fix it. And now he has to do something with it. So imagine one guy, and I'm not making this up. I've seen people do things like that in their code. Observes that because it's weight, the weight can never be negative. So some values of type double are wasted. They are never used. So he decides to reuse them, make some useful optimization. He invents some magic constant, like bogus weight, and now it's clear what to do. We return it. If you get a negative number, it's not a weight, you have to do something else. If it's positive or zero, you have weight. Can you see the bug in this code? And it doesn't have any undefined behavior, it's technically correct. Except I'm sure that sooner or later, someone, when they will be checking if the aircraft is too heavy, will use our function like this. Yeah, the aircraft is too heavy if its weight exceeds the maximum. Except that if we have a lazy load problem and we return a negative number, we say the aircraft is not too heavy. You can fly it. Yeah, we have a database problem. You can go. And if you went to the guy and say you did something wrong, he'll tell you why. What's wrong with this code? I documented it. He probably documented it. I made a useful optimization. I don't need some other means, some other variables. I just squeeze it in. And I'm not the first one to invent it, because even the standard library has a precedent for this. In A to I, when you get 0, it's either an invalid string on input, or it was 0 that we wanted to convert. You never know. My optimization is better because it's clear. If it's negative, it's a bogus weight. It's a database problem, so you should have checked it. And technically, this reasoning is fine, except that it is wrong. Because this guy is trying to squeeze two different categories of information into one type double. He wants to communicate the message that he has a problem with computing the value with the value itself, and it just asks for trouble. And when I see a function called weight returns double, I expect that I should be able to compare it against another double, and apparently it doesn't work. So his code doesn't have a bug, technically, but it is bug-prone. He doesn't have any problem, but everyone else will be having problem when they use his code. And as a side note, someone could say that rather than using this minus magic value, you could use not a number, another special value of type bool for saying that you have no number to return. There is this option, but you don't want to go there. There's many problems related to using those nonce, and one important to our talk is that it wouldn't help solve the problem. If he is returning none, if it's compared whether it's greater than maximum weight, it still says it doesn't, and it will still allow the overloaded aircraft to fly. If you are picky enough and try to look further, you might observe that if he returned infinity, he was even more clever. Now it would work. Infinity is greater than any maximum, so we don't allow the aircraft to fly. But again, you don't want to go there this way, and I will show you one in a minute, in a couple of next slides. For now, the important takeaway is that if you have some irregularity in your operations of a function, you want to reflect this irregularity in the interface, in the function signature, or by other means. If you cannot afford to change the signature, for various reasons, like because you are using it in a hierarchy of classes, you always have exceptions at your disposal. They can go through the interface, and they have no barriers there, unless it's no except, but you usually don't annotate functions with no except. Could he have done better? if for some reason the guy doesn't want to use exceptions, sometimes there are reasons to do that, he could use this boost optional. This is, you probably know boost, and this is the wrapper that says it's either double or nothing. It's almost like returning not a number, except now it's a distinct type, and you can see even from the type that something is going on. The interface itself is sending a clear message that you have to check for something. Now, it's not that good as a previous solution, because the guy did make some optimization, which might have been useful. Now it's a bigger type because it stores both a double and a flag saying whether this double exists or not. And if you're signaling a failure, you probably also want to convey the reason for the failure, not only the Boolean information, that there is some error. And the most surprising thing is that it doesn't solve our problem either. If we forget to check whether this optional is initialized, and we just apply the comparison, it so happens, the way the optional is defined, that this comparison still works and still gives us the wrong results. It will still say that you are good to fly. So we may try to look at other options. Expected wrapper, somebody suggested it at the first talk. It says it's either double or an exception. So we do convey the information about exception. Except it's still bigger than double, and depending on how it is implemented, it was first suggested by Andrzej Alexandrescu how to use this type, and it was saved. The one that is now currently standardized, again, has the same problem, that the inadvertent comparison of expected double with double will work, and will do something else than you think it does. And in the end, if this optimization is needed for some reason, the optimization is fine. The only problem with it was that it doesn't tell you that it's two different things that you have to take care for. So an alternative that the guy can take is to use a constraint type like we've seen in the previous talk. It's still a double inside, except that it's a different type. Even the name of the type sends you a clear message that it may be a quantity or not. And you cannot inadvertently compare it with something else, just a double, because you have to call explicit conversion function to get to the real value. That's it, and you again have the size of a double. So, any clever ideas you have? My advice is, and this usually works for me, talk it with your colleagues. They will immediately tell you that it's not that good an advice. Even if you have invented something ingenious, and it's really good, but your colleagues cannot appreciate it because they don't understand, they will have to use it, and they will use it wrong, and you go back into problems. So unless your colleagues are convinced, you better not implement any clever ideas in your code. It boils down to communication. If you cannot communicate with others, even though you have a good idea, you have a problem. Now I have a question for you. Again, the first person to answer the question gets a prize. We fixed the problem we just discussed. Now we are throwing an exception. There is no undefined behavior going on here, yet there are a couple of potential bugs in this code. I wonder if you can see them. True, there is no meaningful information. Where is the memory leak? Okay, yes. So there is a couple of good answers. We have only one prize. So who was there? You get it. You report later to the organizers. this is a couple I have identified, and they are different. We are talking about quantities, but there is no unit. So if we get a double like 10,000, what is it? 10,000 newtons? Or is it imperial units? You don't know. Perhaps it's not a problem. But in this industry, because we are talking about different aircrafts manufactured by different companies in different countries, we may get into the problem. This was hit by NASA. They lost their Mars Climate Orbiter just because of that. One module was talking in pound forces, the other in newtons. When it was told to descend into the atmosphere, it descended twice too deep and got lost. Also, we are using type double to talk about physical quantities. A double is an illusion that you can fit any quantity there is from a continuum into 64 bits. Does it work for you? It might, but it might not as well. You would have to check it before you just go to using doubles. They are very unsafe, and in many applications you would rather stay away from them and check whether you don't want to use something like rational that doesn't lose information or on multiplication or big decimal, so it keeps all the fractional part. And just the sole fact that you use a defensive if, because it looks like a defensive one, we cannot be sure, but it looks like one, is a problem, because it gets confused with normal or offensive ifs, and it disturbs the reading of the program, which sooner or later will result in other bugs. This is what I was able to come up with to fix the problems. Now, this is not a pointer anymore because getImpl will throw the exception itself. So some of the problems just go away if you report it this way and return a reference that is never null. A null reference has caused many crashes in many applications in many languages over the years. And we are using a different type, again, these constraint types, newtons. It conveys a message even in its name, that, what unit we are talking about. And inside, it is not necessarily a double anymore. It can be any type that suits our needs in this type of a computation. And now some nice examples of exceptions being misused. Apparently, we are not taught exceptions very well because it might be that we are afraid of them or don't understand them, but lots of silly things that happen when you try to use them. Suppose we fix our example from the 10 minutes ago, and we now, again, throw an exception. Yes, it's poor. There is no information involved, and probably it's not us that are supposed to be throwing this exception, but this guy inside. But we can consider it an improvement. At least we don't give false information to the callers. So the guy implements this throw because he thinks it's an improvement. But now he thinks, wait, if I throw an exception, I have to catch it, right? Because otherwise I will terminate the program. I don't want it. So he goes up to this toHeavy function, puts a try, catch, // to do, colon, need to handle it later. And if he's lucky and this application crashes in production, he fixes a crash by crashing the application. This is some idea, but if he's not lucky, this will again, return a random result because it's valid, not to return anything. Some value is there in the registry. It will just be used. If we say it's not too heavy, we are going back to the same problem of allowing the aircraft to fly on a database problem. So suppose he is informed about it and he wants to respond. He observes that it was in the case that we return false, that we risk crashing the aircraft, so he returns the opposite. So as simple as that. Now we are safe in the sense that we will never say you are safe to fly upon database failure. So it's following some principles from engineering that when a system detects it has some failure, it goes to the safest state. In fact, it is the same as we return infinity from the weight in the previous example. We would arrive at the same point where we are returning true from too heavy. And we are, in some sense, safe, except that we now implemented another bug in the system. Imagine how this software will be used by load planners. So the girl sits at the computer. She wants to load something, put some load into compartment. She puts load 7,200 kilograms in compartment 1. The way it's implemented, the application will respond, aircraft maximum weight exceeded, because the other function is returning true there. There's no excess in weight, it's just a database problem, but she doesn't know because it's the function that too heavy that's giving this answer. But what she sees is aircraft maximum weight exceeded. Okay, apparently I loaded too much. She will type something less. Aircraft maximum weight exceeded. Okay, something less. Exceeded. Well, perhaps it's the different type of aircraft. Well, I reduce it further. Maximum weight exceeded. She will go to her colleague, you know, something is wrong. I think it's supposed to work, but it doesn't. Okay, let me help you. You probably loaded too much in this compartment. Let's try something less. Exceeded. Okay, perhaps it's different aircraft. Well, maximum weight exceeded. This will go on until at some point they will realize that the application is telling lies. But it may be after 20 minutes, perhaps. This application is run when everybody is on board, because only then do we know the weight of everything sealed in the aircraft. So we have only a couple of minutes to let the flight go before we cause any delay. If we wait 20 minutes just playing with a computer that's playing with us, we've delayed the flight. This might have caused further delays to other flights. We may have incurred a huge cost. And very likely, it is all done for nothing, this clever fix by the programmer. Because if he was interested enough and went to the upper parts of the application, he would observe that this exception is already handled. There is an exception handler at the top level where you send commands to the application and where it responds that catches this type of error. And because here it knows it's not related to aircraft being too heavy or not, but generally to processing command, it can build an output message custom to our needs. You can also see that I fixed the problem from the previous talk. There is a validate function that returns either the processed command, well-formed, or information about the bad input. It doesn't matter here. What matters is that if you have a well-implemented exception handler at the higher level of the application, you can throw whatever you want from the deeper parts, and you don't catch them at random places. The way it's implemented here, if the guy didn't intervene and type his catch statement, this is what we would get. Someone types load 7,200 kilograms in compartment 1, and it says, yeah, request ignored. We have some internal error. You may use the application, but at your own risk. Now you get the message after the first second, and you have time to respond to, for instance, to reset the application or to do it manually. Now you are telling the truth, and this information is viable. And this guy who put the catch because he was afraid to terminate the program just interfered with a well-working mechanism. And why did he do that? I don't know. Yeah, but my suspicion is that people are afraid of the idea that there is a risk of calling this terminate function, as though it was, I don't know, a terminator that kills you. I hope I was able to demonstrate with these examples that calling terminate in your application is not the worst thing that can happen to you or to the program. It is a viable option. You may come up with a better one, true, there sometimes are better options, but you at least should consider it as an option and not be afraid of this being called. The purpose of any program is never just not to crash. Yes, the programs have some purpose which they have to follow, like giving you the right information about what's going on inside, the results, the information about the failures. No one comes to you and says, well, I want a program that doesn't crash, the other thing doesn't matter. But programmers sometimes really tend to think this way. I must not crash. I must not crash. Not really, it's fine to crash from time to time. It's better to crash the application than crash an aircraft. And the problem here is that the guy was right to suspect that it is possible that there is no catch at the upper level, and his function, this too heavy, might have caused a crash. It's true, but it's not his problem. If we are lacking this catch, and if there is a problem, this is a problem of someone else, not these guys. We are talking about seeing the bigger picture, true, but only to fix our problems in our code. You don't fix global problems locally in your function. So some advice to be drawn from this set of examples. When you're returning an answer, true or false, whether it's too heavy or not having a good answer is not true or false. It's something different. You have to communicate it by different means. And you cannot conceal it. It's a viable information that you have to convene this way or the other. Terminate is your friend. Don't be afraid of it. You need to write those to-dos. I was making fun of it, but usually when you have a branch, you cannot type both branches at the same time. Yeah? You have to decide which one you're implementing first. So there is no other way but just to say this to-do. Put a terminate just down below. It will not harm you. You are at least assuming that you will go back to this to-do, yeah? And then you can remove it. If you forget to remove it, at least you have a terminate to stop the program before it does even more harm. And about catching exceptions, because this is where I found many people get it wrong. When you are in any doubt that you might be concealing some information or preventing some information to reach the other people, because exceptions are a way of communicating from lower layers to the higher layers. And there is a risk that you will intervene with this communication. So if there is any risk or doubt that it would happen, you just don't catch exception. Just let the application blow it. Someone else didn't take care of it up. You will not fix it there in your code. Well, I'm not fanatic about this. There are some valid reasons to catch exceptions. But there are scarcely any places, at least you will find 2 or 3 in the application, where it really makes sense to stop stack unwinding. This is only where you are able to identify a module that is fairly sealed and doesn't affect other modules, where you can abandon part of the computation, just eject it, and proceed to normal proceedings. We've seen one such example before. Usually this is a place where you take a user input and process some command there. You can safely ignore the entire operation, and you are ready to pick next one. This is a good place, but there are not many in the code. You wouldn't expect those catches to be anywhere. And function main. You usually want to catch it there. It's also a sealed module. And if you don't, you are not even guaranteed that destructors of local objects will be called. So only to enable that, calling the destructors of local objects may be a good idea to catch an exception in main. Sometimes this is because how language is designed, or sometimes you have to temporarily deal with suboptimal design, there is reason to catch exception only temporarily to change it somehow, add information, convert the type, but you let it go. And that's basically it. The most important piece of advice here is that even when you work on small function, we should never forget that it will be executed in a bigger context. And we should understand this context, how this may affect other parts of the program or humans that operate with our software. There is more responsibility lying with us than we are sometimes able to see. This is a life-critical application, but there are more applications on which our life may depend. A normal hand calculator, is it life-critical? If a weight and balance application breaks and you have to do the computations manually, it becomes life-critical, because otherwise you are risking crashing an airplane. Or my phone. Is it software that are life-critical? If I need to dial an emergency number, it becomes life-critical. A free source library that you probably write and upload, is it life-critical? Well, if it's used on a calculator or in a phone, it may become life-critical. So you have better make it good. Thank you.